As a teacher, when I teach you something, I teach you my perspective of how I view that particular topic. In the days of ancient Greece, they used to think that a god named Apollo would put the sun on a chariot and he would drive it across the sky. And at the end of the day, he'd put the sun away back into the stable until the next morning. This seemed to be a reasonable explanation of why we had sunrise and sunset. As time progressed, people began to come up with the concept that the Earth was the center of the universe and that the sun rotated about the Earth. And as scientists became more knowledgeable, they began to realize that it was not the sun that was traveling around the Earth, but it was the Earth that was traveling around the sun. And you could suffer penalties if you didn't accept that particular philosophy. So what I'd like to do is take this sort of concept and show you through the concept of zero and negative numbers how I would teach you this information and talk about some of the ways we've been taught in the past and some of the ways we're still and the troubles that we have with teaching this way in terms of what students perceive. And so I'm going to share with you my experience of teaching this material and just having discussions with children to see how they have perceived it and their reaction to it. So let's begin. You have before you a lesson on negative numbers and zeros. And I start the lesson by showing you a number line. 1, 2, 3, 4, 5. I only have 5 fingers, so I've only decided to count up to 5. And that's all that I know about the world. And while I'm doing this, I'm going to talk a little bit about addition and subtraction. So if I would like to add a 3 to the number 2, I start here and I go 1, 2, 3, and I land at the 5. If I want to subtract 3 from 5, I start at the 5 and I go back 1, 2, 3, and I get 2. So we have this concept of addition, which is moving to the right in this line as a model, and subtraction is moving to the left of the line. That's one way that I could look at this. Another way I could look at it, I could say, how are my numbers created? I could say, well, I add 1 to 2, I get 1 to 1, I get 2. I add 1 to 2, I get 3, and so on. So I make the observation that I create my numbers by adding 1 to the previous number. Okay, so at this particular point in time, let's sort of take away with what we've discussed. We've talked about the number 1, and we've talked about addition and subtraction and the relationship. And that is that subtraction is reverse addition. So now let's continue on. And let's now expand upon our number line or our universe. And let's put a number before 1. And I will just call that number Z. And I would say, how do I get from Z to 1? I add 1 to the Z, like I've been doing to the other numbers. So I would have that Z plus 1 is equal to 1, in the same way that 3 is equal to 2 plus 1. But what I notice is I have 1 on both sides of the line. Interesting. Now I come back and I go back to this 3 is equal to 2 plus 1. And in the place of the 1, I put Z plus 1 because they're the same. They give me the same result. And then I rearrange my numbers. I put the 1 next to the 2 and the Z on the other side of the 1. This is called the commutative property. Many students don't seem to appreciate these properties. They know the names, but they really haven't seen them in application-wise. Here I'm actually applying and explaining to it. And then we group these. And by grouping, they said we're going to add these first before we add the Z. And the 2 plus 1 gives us 3. So you use 2 basic principles, commutative and associative, to explain our steps. And when I look at the result, I now see that when I add z to 3, I get the same result. I want an explanation for this. Oh, 0 must be nothing because it has no effect. Wrong. Because I can give you another example that will contradict that viewpoint. And this viewpoint that 0 is nothing has permeated throughout our math. Even the best of mathematicians who instruct will fall into that trap. And we must be aware of it because this leads us on to some serious problems in terms of how we look at other things in math. And I can tell you from experience into talking with teachers and students, there are certain things that they come up with based upon this false notion. One example is when you raise a number to the 0th power. They would say that the answer is 0 because 0 is nothing, whereas more experienced mathematicians would know it would be equal to 1. 0 factorial, another concept. They would come out with 0 when experienced mathematicians know the answer is 1. So what we've done in recent times is we've now given another postulate besides the associative and commutative properties, and we call it the identity property. This sort of begs the question. Now we're no longer referring to 0 as 1, it's the identity property that we call this. Okay, so now let's sort of move on and see what else we can see. Well, on a clock, I have the numbers going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I notice that 12 is the number before 1. And if I think about this, if it's 12 o'clock and I add 5 hours to it, I get 5 o'clock. So 12 plus 5 on the clock is 5. And this would now be one of the arguments that we refute, that looking at it as 0 does not make sense because we know that 12 is not 0 or is not nothing. Being 0 not being another question, but we know it's not nothing. So this application refutes it. And this is one of the things that I'm concerned about, is how we use our manipulatives. Our manipulatives should never be used to prove something. They're used as an application to help us understand it, but not to prove the application or not to prove the concept. So now let's generalize. Let's use a little algebra where A represents any number. And what we've learned from the 3 plus z equal A, and now we're going to let z be 0, which we're familiar with, A plus 0 equal A. And if we look at subtraction as being reverse addition, then 0 is equal to A minus A. Now, what we look at that is when we subtract a number from itself, we get nothing or we get 0. But the reason that that occurs is because 0 is the identity element and subtraction is reverse addition. So when we take a number away from itself, we get 0 as the answer. Not because 0 is nothing. That's the answer we get. Now, I sort of feel a little bit uncomfortable. I've shown that when we add 0 to any positive number to induction, that we get the same number. But what happens if we add 0 to 0? Well, I would hope it would be the same thing, but I'm not sure. So one of the proofs I try is I say, okay, 2 can be written as 1 plus 1. And for each one of those 1s, I can replace it by 1 plus z or 1 plus 0. And so I now have a 1 plus 0 and a 1 plus 0. And I bring the 1s together, the commutative process again, and I bring the 0s together. And 1 plus 1 is 2. Well, I have 2 here and 2 here. So I'm going to draw the assumption that in order for this equation to balance, that 0 plus 0 equals 0. Now, I think we can accept that proof. I don't like it. I feel uncomfortable with it. So I tried a different approach. 0 plus 2 is equal to 2. And I subtract 2 from both sides. And now I know from this little step I did before, or proof, whatever you want to call it, that a number subtracted from itself gives me 0. So I get 0 plus 0 gives me 0. And now I feel much better. Now, what is multiplication? Multiplication is repeated addition. Okay, and what happens is that if I have 5 times 0, I would say that's 0 plus 0 plus 0 plus 0 plus 0. Well, I don't know that's 0. Well, if I take the zeros in pair, I replace these two by a 0, these two by a 0, because of the rule pair, and I would then have 3 zeros left. And of those 3 zeros, I can replace 2 of them by 1, and now I have 2 zeros left, and then I have 0 plus 0 is equal to 0. So I'm going through a logical process, not jumping to conclusions. Then I could come up here and say, well, what is 0 times 5? Well, you'd say 0 times anything is nothing. But I'm not accepting that argument. I want another way using what the foundations I've given you already. So one way that I could do this is I could say, well, what is multiplication? Now, we usually look at multiplication as repeated addition. You'll notice I have a 0 there. But so 3 times 2, we normally think is 2 plus 2 plus 2. And one of the students I was working with, his teacher was saying, well, to explain this to you, we do skip count. 0 to 2, 2 to 4, and 2 to 6. And there are 3 jumps in there. Well, my question is, why did you start at 0? Why didn't you start at 2? Because if you took your 3 jumps, then you'd end up at 8 and not 6. Okay, well, we know that 8 is not the answer we'd like, 6 is the answer we'd like. So that would be why we started 0, but we could also start at 1. So instead of defining multiplication as repeated addition, where we just repeat that number of times, I'm saying it's the number of times we add the number to 0. And now this is not a proof, but it's a sort of an induction process. 3 times 2 is a 0 with 3 2s. So if I had 2 times 2, it would be 0 with 2 2s. And 1 times 2 would be 0 with 1 2. And 0 times 0 would just be 0. Just what I would expect. Now, as I said, I don't consider this a proof, but what it is a validation process. It makes me feel comfortable that the commutative property really works. So as you can see, I'm now looking at things in a very different way, and I'm even explaining some techniques that other teachers may have used. Okay, now, let's move one further. Okay, I put A and B in there, and for those of you in the know, will know what A and B are. But right now, pretend we don't. Well, I know if I add A to 1 to A, I'll get 0. And if I add 1 to B, I will get A. And when I've taught this to students, I'm impressed. The fact is that they have absorbed the rule in this short period of time and are actually able to apply it. Okay, and then I say A plus 1 equals 0. And later on, B plus 1 equal to A. Well, since subtraction is a reverse addition, I move the plus over, it becomes a minus, and the 1 over here. So I get A is equal to 0 minus 1. Well, we don't usually write 0 minus 1, we write negative 1. And this is what I call notation. I called it A before, but here we call it minus 1, and we sort of describe the process we got it. We just basically threw the 0 away. And if I put the minus 1 back in the place of A, I get minus 1 plus 1 equals 0, which I'm going to tell you is what my definition of a negative number. When a negative number is added to its positive inverse, you get the identity element, or 0. And now let's look at B. We had B plus 1 was A. Let's add 1 to both sides. Now these become 2 when we use the associative or commutative property, or addition in this case. And we know from up here, A plus 1 is 0. Okay, so we can put a 0 there. And if I now subtract and put the 2 on the other side, I get 0 minus 2, which I will call minus 2. And minus 2 plus 2 equals 0. And now you can see where I got my definition from. Okay, we know that 0 plus 0 is equal to 0. And if I move 0 to the other side, I get 0 minus 0. And we know from this that when we subtract a number from, we get 0. But I go back here, look at the pattern. Minus negative 1, negative 2. So I would get minus 0 for the answer. And what I see is that minus 0 is equal to 0. Okay, so what we've now gone through in this process is we've now shown how we are deriving things and doing it differently than we were taught. And how all of a sudden we now have an explanation. We're just told what negative numbers, where they are. And we're told, in some cases, my students have told me that they're told that negative 0 doesn't exist or it's not a number. What I'm showing you here on the number line, when we write the number line, 0 and minus 0 occupy the same space. Okay? And these help us understand better. So now, take this information, look at the way other people are teaching, as I've done, and you will be very surprised at how they come at what they do. And then the question is, do you accept that method of teaching or not? So this is the challenge I'm giving you to look at. Now, I don't have time to do the rest of this, but here I was talking about how we can show that 11 on the clock is like negative 1. It doesn't have a sign to it. Okay, and the reason we say because it has the same properties that a negative number has when we add it on the clock. It's like subtracting. And then I go through and I show how we derive some of the rules for negative numbers. So for example, when we subtract a negative number, we make it a positive number and we add. And it comes from our definition. If we move the 1 to the other side, we get our definition for negative number. It falls from our definition, even though we did it backwards in order to derive this. And then we just look at the 1 and we get this inverse operation. We're discovering something new. All this without saying that 0 is not nothing. And then I go through and do different proofs over here to show that when we add negative numbers, we add them as a positive number and make the sign negative. When we subtract a number bigger than another number, we subtract the smaller from the bigger and make the sign negative, all basically by going through a set of proofs. And then I use another manipulative, in which I use blue and brown pennies, where a blue penny represents a negative 1 and a brown penny makes a positive 1. And I have a special rule that when these two are put together, they give you 0. Okay, which is what I basically had before when I was defining my negative numbers. And so now with this rule, I can show you different tricks in order to add and subtract numbers. But one of the reasons, or another reason I don't like manipulatives, kids will tend to use this to solve problems. Well, it might be useful to solve this with 2 or 3 pennies, but not 1,000 pennies. So basically, it helps reinforce it, but it's not something to be used. So we can then go further on multiplying by minus 1, and I will take a little bit of effort to do this one, because in this case, I have seen some gross mistakes, in my opinion. And so, again, what we look at is we now have to push our imaginations. And we're going to say when we multiply 5 times a negative number, we're going to have 5 of them. And from the rules of addition, which I didn't go over, we can show that when we add negative numbers, we add them as a positive numbers and put a minus sign in front of it. And then I get a little bit lazy. I don't go through the same thing I did with the 0 to show what happens when I commute them. But I'm going to assume that this works. Okay? And sometimes this sort of illustrates the limitations in my comprehension of what's happening. So a negative 1 times a 5 is a negative 5. Okay, and now let's take a look at what happens with our proof over here. And what I'm looking at here is, I'm looking at this as another way to try to understand this. 2 times 5 is 10, 1 times 5 is 10, and 0 times 5 is 10. You'll notice I keep subtracting 1 from this number. So if I go down to minus 1, what I notice I'm subtracting 5 from each answer. So if I subtract 5 from 0, I get minus 5, and likewise, I get minus 10. So this is how I feel comfortable that when I multiply a negative number times a positive number, I get a negative number as an example. So this is a validation. unless they consider it a proof. And then I take this further and I say, if I start off with 2 times -3, now that I know that a number multiplied by a negative number is a negative number, I get down to here, and when I go negative, all of a sudden I see that my numbers start going positive. So the negative number times a negative number is a positive number. Surprised. This one I like too because it takes, I don't know what kind of intuition I'd have to have in order to be able to really comprehend this fully. And so now we start off with -3 times 5 minus 5 is 0. And I didn't prove this, that at 0 times a negative number was 0. I leave that to you as an exercise. But I don't make the assumption that this is true, as you saw before in my proofs. And now I'm using the distributive property, negative number times 5, negative times a negative number. And now what I do in here is I leave these 2 negative and move this to the other side. And when I subtract a negative number from 0, I get a positive number. And that's the proof that a negative number times a positive number is a negative number, avoiding making the statement that 0 is nothing. We could go further and show how we could discover the imaginary number. All of this from just some simple little operation. And here I've now summarized what we've done. My interest was basically to show you the concept of 0 and negative numbers and just show you how being taught with different ways leaves us with impressions that will make us do math incorrectly or not allowed to understand it. Happy that you will let me into your homes for these few minutes so that I could express my viewpoint on how math is being taught. Hopefully you appreciate what it was done, and my goal has been to make it, to encourage us to try to understand math better so that we can teach it better and empower our students. The lesson that I showed you, I've taught to second graders, and they've been delighted in the surprise that come out when I teach them this. So if second graders can begin to teach this concept, imagine how easy it is to teach it to third and fourth graders and seventh graders. Thank you again. Bye.